Hello everyone, and we're back here on AtCoder. This is AtCoder Beginner Contest 331. As usual, check out the other videos on my channel, and as well in the description there's the frequently asked questions section, so you can check out if you're interested in what plugins I use or some other things. So yes, as usual we are using the CPH Judge extension and the competitive companion extension. This is the most asked question. But okay, so let's go and solve the problems. The problem in calendar exists of 10 months. Each exists of the days. What day falls here this month in the calendar? Okay. So this is just what day falls here this. Okay. So we just take months, days. I'll just zoom in a little bit so you can guys see. Okay, and then year M1 D1, year M1 D1, and then we want to add D1 if D1 is bigger is equal to D is equal to D plus 1, M1 plus if M1 is N plus D, then D, of course D1 has to be reset. This is year plus plus, and then M1 is reset to 1, the first month of the next year, and then it's printed in the Japanese form year, then month, then day. Okay. Sells egg packs. A pack of 6 eggs costs SEN or 8 MEN and LEN. So when you can buy any number of each pack, find the minimum number of money required to purchase at least n eggs. So because n is very small, we can purchase some amount of. We can of course use DP, but this problem is not intended for DP because n is very small. S, M, and L. Oops. So what you can do is like you can brute force. You know that at most 100 packs of the small quantity, at most 100 packs of the medium quantity, and at most 100 packs of the large quantity will be bought. Then the amount of eggs is of course contained in this is of course I times, so I times there's 6 packs here, then J times 8 plus K times 12, and then if X is bigger than N, then there's of course what is the cost here is the cost is how many I have bought times S, how many times M, and this is times L, and then this cost will be, so there will be some answer which is like maximum, and then the answer is the minimum of answer of this cost. this is how you call the brute force. You're given a sequence of like that. For each f, solve the following problem. Find the sum of all elements in A that are greater than AI. So for each of these, we want to find some sum that is greater than AI. Find the sum of all elements that are greater than AI. We can of course use Fenwick Tree, but yeah, there is some other solutions. Probably just sort and go. Yeah, so the most basic solution I would think is there's this answer array, I would say answer, and then there's some other b, let's say b is equal to n, to a first, then we're gonna sort, it's actually not, b is going to be a pair of int and, where b of I will be equal to a of I and then I. Then we're gonna sort b in decreasing order, so we're gonna start from the, then I'm going to have a running sum, then I will go through all of b and I will say greater, so I'll say at the end I will increment the sum to b of I dot first, this is our element, but at b of I dot second, at this answer, the sum is this, and then we just want to go through the answers and see how that. Sort or begin. Oh yeah, this is the, okay, so we cannot sum them if this is the same idea, so there should be some running sum, and if b of I, so L running some value, and then, okay, so the idea is that if b of I dot first is equal to the running sum value, then running sum plus equal b of I dot first. So we just remember this. Else running sum is equal to b of I dot first, running sum value is b of I dot first, sum plus equal running sum did I miss something? b of I dot first is the running sum value, then we just increment the running sum. Yeah, the value should be b of, this should be the value. the bi is equal to the running sum value. The running sum is increased. Otherwise, this is summed up. So this is when you encounter a smaller value. You encounter a smaller value, then you say yeah, this is not correct. This says the following. Greater, yes, this is correct. Then if the running sum, yeah. Yeah. Here it is whether BFI dot yes, so this is the idea. If BFI dot first is not equal to the running sum value, and then we want the sum to be incremented with the running sum. Else running sum will be the this. I think that should work. Okay. There's a grid with a large number of squares. Each square is black or white. The color of the square is represented by character mod n. Mod n is very, so it's like repetitive. Here, okay, answer Q queries. Each query gives you 4 integers. I should find the number of black squares contained in the. Oh, I knew that there would be a wrong answer somewhere. Let's see. Wait. Oh. So this here just a little bit of math. How many? It's just a little bit of math. Let me fix see. Is there? With the Fenwick Tree, I would have solved this very quickly, but so we have the running sum. Is there overflow somewhere? So if this is not equal to the running sum value, then the sum is incremented. So if we're not adding here, then the sum is incremented by this, by the running sum, and then this is added to the value. Okay, that's correct. And the sum is here. But then this running sum, but then if it's equal to the value, it's added to the running sum, it's not incremented. And here it is incremented. Here it's like written the answer. Oh, there could be a long here, right? The answer could be long. Yeah, the answer could be long. Okay, that's That's a stupid mistake. So it could be long, these are fine. So yeah, so this is just we do DP first. We run some DP. Very I mean it's no problem. It's no problem. But we have to be a little bit careful with it. So there's NM. There's this pool, or just we could do just integer array. And then we just read some string. If ij is s of j is how many black squares? How many black squares? Okay, so now we just need prefix sums here. And that's like the aij is if j is equals 0 and I is equals 0, we continue. If j is equals 0, we say a of ij plus a of a of I minus 1j. If I is equals 0, if ij plus equal if ij minus 1. Else the a of I j is equal to a of I minus 1j plus a of j minus 1 minus a of minus 1 j minus 1. This is our DP. So in fact our DP, okay, so we have this prefix sum table. Then okay, so we have some prefix sums. We need Q queries, right? Oh, M, this is Q actually. So int M is equal to N. Okay, so for each query, we have to do something. So for each query, it's, let me just see if it did this passed, as this passed. Of course, this will pass. Each query, we will do the following. So we have A, B, C, F. I'll do this. Maybe just for the clear. Clean code. Okay, so we have to there are some rectangles that would be in like the whole thing, and then there's like the boundary that won't be whole. So it's like if I draw this, it's a little bit like that. So there's some, so all of these, let's say like these are the rectangles, and then you start from here somewhere, you end up here, you end up here, and you end up here, like this. So this would be whole. Then what you need to calculate is this, 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 and some amount of this thing. So there could be more of these, and like let's say here, so this, let's say some other. There's how many different? There's a bit different. So how do you pull this off? What if I know the corners here? So okay, first we need to calculate how wide and this is. So to calculate this, you need to go to the next one, here, and here to the last one, and calculate how much is this. Or just yeah, you need to do this. You need to x1 plus x1 minus plus what we are dividing, this n minus 1 divided by n new point 1 in new point x1 plus n minus 1 divided by n, and do this for the second, but the second we're not going down, we're just going like this. Okay, cool. Now this is so now the difference between the width of these squares here, the height of these squares is the difference between this and this. I'm not sure if here should be +1 or should be +1. That's a problem. That's a huge problem we're not sure of. Okay, so that's the width. Then so let me just change this to overflow something. Okay, so that's this, right? We know now what are how wide and long is this. I think here should be +1. I think should be +1, but I'm not sure. Maybe not. Okay, so width height times width times, so the answer is height times width times a of n minus 1, n minus 1. This is all. We're getting all of them. So that should always. Okay, so this is not plus 1. Okay, that's not correct either. Okay, we are. Oops, wait. No, that's correct. XY. Wait. E of I minus 1 minus 1. What is this? 4. There are 4 blacks, that's correct. There are 4 blacks, so width times height. So width times height. The width is wrong something. So therefore oh, okay, now that makes sense. What if I add plus 1 here? Oh, that's not plus 1. I don't think that's plus 1. I think that's plus 1. Okay. So we add this, then we want to say that want to add this. So how do we add this? So we need to query out there's this, I will call this X and Y. Let's do X and Y first. So there's this area X, I will call this. Area X is the sum. Area X is the sum of all of these minus the sum of where this X starts. But minus 1 here, so let me do a function here. Let me do a function so I can avoid so if X is smaller than 0, return 0. If Y is smaller than 0, return 0. If if else should be returned a of x1. I think it's correct. Okay, so first x1 has to be modulo n, and this has to be modulo n, and this has to be modulo n. 2 has to be modulo n as well. So there's the sum of, so these here that I'm referring to x's, actually this point here is the following: n minus 1, and then the y is equal to this y here. Well, let's have implementation of task y 1 minus 1. That's the sum, right? That's the sum that is here, but x, the area of x is sum n minus 1 minus sum this, right? Okay. Area of y, so the whole area minus this. So the area of y is another thing. The area of y is the same thing here, but minus x1 minus 1, and this is n minus 1. So area of y, area of x. Area of x will be height times the height plus area of y times the width should be added to the answer. And now the answer should not overflow our required answers. That's correct, and that is correct. Okay, it's still in the boundary. So we covered these, but these are now the corner squares are a little bit off, and essentially the corner squares should be added here. The corner squares is, this square is kind of bad. Okay. The square is essentially x plus y no, this square is a little bit hard to compute. This plus this minus this. So, or in other words, it's this, what we had, sum of x1 of n1. Okay, so first corner 1 is sum of n minus 1 y1 minus 1. That's this sum plus sum of x1 minus 1 n minus 1. That's, so we have this sum, we have this sum, and minus this, so minus sum of x1 minus 1 y1 minus 1. That's the first corner. The second corner, which corner should we take? Let's take this corner here, the second corner. Second corner is x. What is this? So this here is this sum minus this sum. sum of x1 minus, oh, this is not, oh no, this is sum of x2, oh, this here is sum of, so onto this sum here, x2 and then n minus 1, x2 n minus 1. Okay, so this is the sum minus sum of this here. So so y2 minus 1 is in this direction. No, not y2 minus 1. Oh, shit. x1 is this? No, y1 is this. y1 minus 1 in this direction, but in the other direction is, this is y1 minus 1, and this here is x2. Oh, C3 is, alright, so it's this piece of thing here. So y2 and n minus 1 minus sum of, and here would be x2, x1 minus 1 and y2. And the fourth piece, the final corner, is just the sum of x2 and y2. And the answer should be added to these four corners as well. Now I think we're good. Oops, we're not. Some corners now. So here we're making more. Just maybe this corner. It's on this corner. Am I using this correctly here? Here there should be 0 h and y, I think. But there's one here, wait, y. 0, 3, 4, 5. 0, 0, 3, 4. No, there's something wrong here. x1 h is wrong. The height is wrong. Okay, H is cool. H is cool. What if there are no corner pieces here? What if they say that, what if this here piece is not a corner piece? That's the problem. I think that's the problem. What if this piece is not a corner piece? So that means that this is either, so y1 is not 0, and then or x1 is 0, then this is 0. So here it's about, here on this corner it's about either having y either having y x2 to be 0, or y2 to be n minus 1. Is this correct though? Y2 to be n, and then, oh, this took a long time. What are the standings? Wow. Corner 3 is this guy here. It's, we don't count it if x1 is 0, or if y2 is 0. y2 is 0 or x1 is 0. In this corner, in the last corner, we don't count it if y2 is n minus 1 and x2 is n minus 1. Wait, this is not correct. When do we don't count this corner? The first corner here, we don't count if this is, if x1 is 0, or if y1 is 0. Second corner is if x2 is 0, if y2 is 0, or if x2 is x2 is minus n minus 1. Yeah, we get area of X and Y, but we don't include these areas too. We have to include these areas as well. AX2 is like this is 1, 1. But then there's something here that also includes, and that's the fact that come on, there's a lot of sums here. That's x2 sum of x2 and then y minus 1. This is the y area. Ax2 is the sum of n minus 1 y2. Then this should be added here as well. Now the corner pieces are not really correct, right? So if I discard the corner pieces, would that be okay? It's not okay either. Am I overcounting something? I could be overcounting something. How do you implement this pattern than just looking at every edge case? Oh, I could just, I mean, no, I can't iterate. Queries are too much, right? I can't iterate. You have to look it up like that. I mean, okay, I will finish this. I will solve F first. You're given some string, process cook queries in order, change the X character of the string if the substring formed by this palindrome parent, yes or no. Okay, this is a kind of cool statement that I have seen before, and it kind of, I think, involves okay, no, that was another statement with like a. Oh, actually, this is just a hash, right? Like you have two hashes, and then you just see that they're equal. Yeah. So yeah. Okay. Cool. You have a hash bit, right? Let me pull up my algorithms. Hash. Hash. Is it hashing? Fenwick Tree and hashes, right? Don't I have it here? I certainly don't have it here, but I have it somewhere here. Hash bit. Hash bit. Okay, that doesn't really matter. Yeah, of course we need some. So I will just make it smaller so I can see better. Okay, so there's. Okay, L with this, blah 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 blah. Then there's this hash. Okay, so we have two hash bits. Hash bit HB, and this HB should be, there's no initialization, so HB and HB reverse, and then HB init S, and then string T is the same as S, but we need to say that T dot T reverse T begin T end. Okay, let's do this. So this HB reverse is the init T. So we have from the start and from the end, and then each query is essentially of two types. If type is 1, if type is 2, if type is 1, we just change the bits. So there's X and character C. And then we want HB dot set character at position X to C, HB reverse set character at position N minus 1 minus X to C, right? And then print here LR, and then we need to say the following: L HB, so alt hash hash is HB dot query dot get L, and then L minus minus R minus minus L R plus 1 outer hash reverse is HB reverse dot get, and then this is the reverse idea. So wait, this is correct, right? So we do this, and then yes, so we N minus 1 minus L, and then N minus 1 minus R, then we add plus 1 here, I think, and then we say we just need to print if hash equal hash ref, yes, otherwise no. Maybe here's something wrong. L n minus 1? No, it's from the start to the end, but this is from this to this, I think. Yeah, okay, that works. I think that should work. If they don't have tests against these hashes that we're using, but okay, gets accepted. Nice. Okay, so okay, this should get us a little bit at least something points, because F should be very hard to solve if you don't know this technique. Cafeteria sells meals consisting of main dish. There are n types of main dishes. There are m types of side dishes. A set meal is composed by choosing one main and one side dish. The price of a set meal is the sum. However, there are L distinct pairs. The set meal consists of this and is not offered. Won't go well. So there's this many offered. Find the price of the most expensive set meal offered. This already looks like some kind of match. But I mean, or some kind of segment tree. Okay, so these do not. Um, hmm. If AI would go to 10 to the 6, you can do like FF tiers. I mean, you can just iterate, try to find this. Okay, what about bind search already answered? Is there a pair bigger than some answer? And to find pair bigger than some answer, you just need to what about okay, there's some edges between the side dishes and this that do not go well, right? So there's the main dishes, main and side. And okay, you say there's some edges that do not go well. These do not go well. But okay, we're going to sort them in increasing order. But here, if I want to pick this, I can pick any of the other. So essentially I always want to pick this and the biggest dish that is not. So for each dish in N, I'll take a look at the biggest dish that I can pick in L that is not, and then I can just maximize this probably. Okay, so just do that. Let me just see, there's N, L. Oops. But how do you find what is the biggest dish? So for okay, so we said for main thing here, I do okay. We're gonna iterate them all. We're gonna iterate them all here main. So we don't need to sort them, but we need to sort the side dishes. For each main, I'll say what is the largest side dish I can take. Right, and the largest side dish I can take is I can just binary sort. Okay, so how do we implement? It's a bit implementationally heavy, I would say. So I will sort B. I'll sort it in decreasing order. B is BD. BD of I is B of I. And then I can sort BD. Sort BD in decreasing order. Now I know I need to map something, and this is like a map BD, and now that we have the order, map B of BDI second, so this it's now I, and then when I read the pairs of dishes that are forbidden, there's main and side dish. Side dish will be mapped to the side dish because now it's sorted. And then P of I is main and side. Now it's sorted. Now the answer is 0, of course. And we want now B is sorted. So we will be using BD all the time. So for each main dish, so the current goodness is if I take the main dish only, but okay, so for each main dish I will actually do this vector of this, and then this is L, and then P main pushback side. So that's the graph, our graph, and then the main for side dishes in P of I. These are the side dishes that do not so the best side dish is of course if I can take n-1. I'll sort P of I from reverse, and then if side is best, then best minus minus. But then there's an idea that this is not the case. So side is not the best. So there's already best, which is possible. Best is possible, and then if best is possible, the answer is the max of answer, and BD of best of first plus whatever AFI. So this is the main dish plus whatever the best was here. Of course, okay, log1 side dish. Now let's see here. 0, 0. Oh, we reverse it in the decreasing order, which means that the best dish is 0, and then I need to dig in increasing order with this, I think. This here is what? There's one dish here, there's 0 else. Of course, we have to say that, okay, if there's no side dish, then the best is 0. So we have to also kind of maximize if best is smaller than m, we kind of want to maximize this as well. Okay, that's oops, what? Adding this and deleting this changes the answer. Excuse me, what? Uh, M. But BDI second should be filled. Okay, I don't know. What? Shoot. How can I see how to change the way? Something with memory, something with memory. P of n, push back n, best I can, best first if I. So we just here as break. There's something wrong here. I don't. BFI second. NML, this is red. BD is okay. I don't get it. I don't get it. B, D, best first. I told you I'm baffled. I'm baffled. How is this even possible? Let's go over the code once more time. This is fine, right? BD. There's no overflows here, right? Okay. Okay, let's go over it one time. BDM, BDI, be by sort. The map is long A. This here comes from here, which is limited. Should be fine. Then there's this n vector adjacency, right? And then get the main and the side dish. The side should go through the map. The main dish doesn't change. Go over all the answers. This best plus plus. Best plus plus answer. Oh, such box should not be made. Okay, now it's only up to D. We'll solve D. What about G? There are n cards in the box. Each card has written an integer. There are CI cards with the I written on them. Starting with empty, repeat. Randomly draw a card. Write an integer on the card in the box and return the card to the box. Find the expected value modulo this. The number of times the operation performed until the notebook is all m. So there's all integers from 1 to m written at least. For each, there's CI cards with that number written on them. CI cards with that number written on them. From 1 to n. Expected value of so there's one card. What is the expected value? Find the expected value of the number of times the operation is performed until the notebook has all integers. Expected value of the number of times the operation is to be performed. So there's so this is weighted, but let's say it's not weighted, it's uniform. But when uniformly that makes something easier. Something's easier. But like you have what is the probability that you have this is the probability that when you have some zeros we care that what is the probability that we have one? How many ones are there? So there's some number of ones. If I get so zeros over n is the probability that I get to the next transition. So there's zeros over n of value. So if the DP is constructed in the following manner. It says TP of. Alright, this is a very hard problem. We probably involves some sort of FFT or something. This I think is hard problem. Let's just write the. Is there a better way to get all these edge cases down? I think there is a better. So I have to solve D in order to get rating. Okay, so what am I missing here? So is it overflowing already? It's already overflowing. So the problem with this is what we had here is, okay, I have this box, but what if this box is the same as this box? Then we're like kind of twice counting it, right? So this is if y2 is not equal to, well, not y2, if it's not in the same box. So because we have a module here, this is not correct. Oh, we can do this. npx this is what area is this? This is this area, which means that this is why npy1 is equal to npy2, then this is 0, otherwise it's this. And npx1 is equal to npx2, then this is 0, otherwise it's this. Then we have to add on top of this, but this is not correct as well. There can be edge cases. Can I brute force this somehow? Is there a better way of doing this? Because they're 1000 by 1000, can I say, okay, if x1 is somewhere here, can brute force for, no, there's no way of saying, it's too much. But then it repeats somehow. There's a case where hate problems which have edge cases like this. Just implementation. There's a case where this is the, like, here you see this and this, only see the corners. Okay, what about where it's like inside? there's no corners. What about if there's no corners like this? Who thought of this problem? We have to cover all of the edge cases. We just have to cover them. I don't see another way of doing this. I would more likely want to solve G. Okay, so I think I have covered this here. And I just need to cover what if there are no... So, okay, so I covered this, right? And then I have to cover that. What are these areas here? These areas are this here, right? So what if this here is... No, the corners are not even included here. We just include this. We just wait. What was saying? Okay, so this here is over done. Okay. Hmm. Hmm. Huh. If this is the whole thing here, then like if y1 is already 0, then I think this should be 0. x1 is already 0, I think this should be 0 as well. Okay, that kind of fixes this issue. But now the corners problem. Corners is a big problem. The corners, when this corner exists. This corner exists if it's not this, or it's not somewhere here. It's not somewhere here. So if it's not like on the edge. Like there's the idea that what if it's like in the same, if what if they're in the same square? If it's like in the same square, we just what if they're in the same square? Same square. Maybe that's not it. Maybe that isn't should be equal. Okay, so if it's the same square, then the answer is the sum of x2 y2 minus the sum of x 1 minus 1 y 1 minus 1. No, this is plus the sum of that. But here minus the sum of x2 y1 minus 1 minus the sum of y2 x1 minus 1. So that's, and then because we're twice, we need to overhaul that one. And wait, what? Oh, we need to do that. x2 y2 x2 y minus x2 y minus 1 x 1 It's all in 3 minutes. I have to fix this. Why? Well, that's not the same. It's not the same square. That's out square here. Oh, wait, this doesn't work. This doesn't work. I have to calculate another way. Okay, I will just leave that task. Collect all. How do you solve this? There's the weight. There's the weight. The problem is the weight. And the problem is that, like, you probably need some kind of fast Fourier transform to do that. Because matrix exponentiations are possible. The sum is equal to n. Oh, so the cards are, so there are at most n cards. So each card is essentially saying that, okay, there's more probability that this card will be, but that does not. That the sum of the, I mean, not kind of sure what you are supposed to do there here. Number of operations performed. If the number of operations, so you have to look up here if this is uniform. If this is uniform, the next transition is this. So dp of I. So dp of some ones and zeros is dp of less. So we just change like how many ones do we have. So less ones, the same amount of zero. I mean, zero is now plus one, but so I don't need to have this here. So dp of ones, dp of ones times zeros, which are like n minus whatever ones minus 1 we had over n, right? So this is like our zeros, and then so that's kind of a recursive thing, right? But now instead of, okay, but that's linear, that's uniform. If they're uniform distributed, the weight of each of this is uniform. But now there are more cards here at this one than there are cards here, let's say. It's not really simple how to do it. But let's just read the tutorial here. So there's by inclusion exclusion principle. Yes, so interpret on polynomial. So it's, I mean, yes, of course, some kind of FFT, and the Markov chain is well, okay, that's that I have to look up. The exclusion inclusion principle is not that. I mean, it's not that one, but the Markov chain one is probably way cool. Okay, so let's go over the tasks one more time. So I wanted to look up how is it. Okay, that's, I mean, how do they divide it? Do they shift it? Wait, what about the what? Do they recursively compute it here? That's pretty clever, actually. What is G of IH? This is the starting point. This is the ending point. We want to make this character. So he computes it. He computes for this. Then yeah. So I see what. So he does one more iteration on top of this. What we had. Okay, this is pretty clever. It's pretty clever. And it's much simpler than what we did, right? It's essentially just saying that I will compute the whole thing, then I will minus this here, plus this here. And because I all compute them as a prefix, it's very easy to say that it's very easy to compute them. Kind of cool problem. I mean, cool problem, but okay, I'll upsolve it. I'll upsolve it later, and I will take a look at G. But okay, so let's go through all the problems one more time. There's the calendar problem A. We just add on the day, and then we check if the month is increased and if the year is increased, and we print that in the format of Y, month, and then day. Just two checks. Just that's it. Problem B. Of course, problem B can be solved with dynamic programming. Up to the so up to n, very efficiently. But one can see that n goes up to only 100, and then I can iterate over like the at most 100 boxes I will ever buy. So I need to iterate over if I buy 100 small, 100 large, 100 medium, 100 large boxes, all of these combinations one can iterate, and but this is how many x I will get. If x is greater than n, then the cost I will calculate, and then the answer is the minimum of all of these costs. Of course, this is a totally inefficient solution, but it's quite quicker to compute it, and quite quicker to write than the DP solution. But the DP solution, one can train on the DP solution. So we can even write the DP solution right now, but we kind of oops. Let's see. I don't know what is going on. One can turn on the lights. Yes. Okay, so C, you're given some array, and then you want to find the sum of all elements in A that are greater than AI. But because we can answer the queries offline, you can use Fenwick Tree, and you can do it this way as well. But you can sort first all of the elements in decreasing order, and then have this running sum, which says that okay, for our current element, we're going to put that in the running sum, because the current element could, like, you could have multiple equal elements, and these all equal elements should be put first to the running sum until there's an element smaller, which then all of this running sum will actually, like, the sum will get all of this plus, and then it will be reset to that element. This is just to avoid the multiple equal consecutive elements. One can probably like do some kind of a frequency on the elements as well, because the elements only goes 10 to the 6, so that is another solution you can pull off quite quickly. But that's pretty much it. So D, we looked up now the tutorial, so you don't have to write all these edge cases for D. Just you recursively solve the problem, and the tutorial is pretty well explained. That is essentially what we were doing here is we were dividing into the group of edge cases, where we first have corners, and then we had this, but the tutorial wants us to do the following, and essentially if there's 2 points, which are this A, B here, and then here C, D, what you want to calculate is always up to the, you want to calculate this from 0, 0 to, want to divide it like this essentially. And then they say, okay, there's this what we want to calculate, right, from A to B, but in order to calculate this, there's this another function that you calculate first this minus, so this is A, B, or let's say this is T, U, V, and W, and W is essentially going to be equal to all of this, so like all of these minus, so this is let's say some function, so they say some function CD, this is from 0, 0 to CD, minus V minus U, but T has to be added once more. And these are all functions that can be denoted from such like this. So from 0, 0 to this point here, or from 0, 0 to this point, or from 0, 0 to this point from AB. So T is just G of AB. And this might be a little bit more complicated. It's like C of U will be like A and then D or something, and then this would be C and B. So these functions, but then G, to calculate G, this G function, if I have this here, then one easily can, I think, easily can calculate this G function. You just need to know how many of these are full inside and then something left over, and then the same idea is how many of like these are full inside, something left over, and then when you have something like this, then you count all of these that are full inside, and then it's something left over, but recursively call this here. So just like recursively, it like recursively calls this function multiple times, but it's constant. I mean, yes, okay, it's a cool problem, but not very interesting one. The problem E was about having so just for each of just seeing that you can iterate through all of these n main dishes, and for each main dish I want to find the most expensive side dish I can combine it with. And I ordered the side dishes in decreasing order. So here the side dish is in decreasing order, and I have this kind of a map where this is now changed because this side dish has new index, and then here I create a graph where for each main dish I said what side dishes I can't eat. And then for each main dish, I get the best side dish first is the 0th index. I sort what side dishes I can't eat in increasing order, and then if I say that if the side dish that I can't eat is equal to the best dish, then I increment the best dish to the next one, and I do that all the time here but this is because this is only the sum of these two for loops only go to L. So this is only O of L. And then I check here whether or not the best is smaller than M. So because sometimes with one main dish I cannot combine any of the side dishes. But if I can combine some, then I combine it here. So this is the main dish and this is the side dish. And that's pretty much it, and you maximize the answer over all of these. So that's cool problem. It's a likely problem to see at some like easy Olympiads or something, something like that. However, this palindrome query problem you're more likely to see it on ACM contests because it requires hashing and all of these ideas. But essentially, you are using this hash bit function. Right, and then the hash bit function, the hash bit data structure is essentially like a Fenwick tree, right? So these are the, how do you say it? Is it the rolling hashes? Like where you have like prefixes and then it is possible to, with little bit of math, it is possible to create a structure where you get where you query an interval because it's commutative. So yes, I mean it's possible. the module allows us to do that, but it's possible to query an interval and get a hash. And this PLL here is just a pair of long. Because we're not only querying for one hash, we're querying for two hashes. So on each interval, we're getting two hashes out. This is just to avoid collisions. Just to avoid collisions where where the strings won't be equal, but they have the same hash. So you want to get two hashes. You want to get as many hashes as you can, really. Like if you do like 3 or 4 hashes, and the probability of collision is just probably close to 0, right? I mean, it's so 10 to the minus 30, 40 or something like that. So essentially, you're here querying this, and then of course you can set something. You can change a character, and then what I do is like to query for palindromes to see if they're equal. What you can do is you can have one hash table, which one Fenwick tree on hashes from with the original string, and one with the reverse string. And then when you do that with the reverse string, you essentially want to change the original and the reverse appropriately. And then when you query one hash from the original and one from the reverse string. And if the original matches in the same interval matches with the reverse string, then this is a palindrome. If not, this is not a palindrome. So kind of an very interesting problem. I wonder if there are some other segment tree solutions. Yeah, so yes, you do hashing, but what is like? I mean, yes, so they're using segment tree, but also this can be pulled off with a Fenwick tree as well. But is this? Yes, so they keep two hashes. They keep two hashes. One is probably reverse, and one is the straightforward, and one is the reverse. Yes, that's pretty much it. Cool problem, right? Collect them all, just some kind of polynomial multiplication problem. I have to look it up. I have no idea how to get to the solution. So yeah, that's pretty much it for today. Thank you guys so much for tuning in, and I see you in the next Codeforce or AtCoder round.